Hi, and welcome to another video by the Writing and Tutoring Center. Today we're going to be talking about finding the electric field of an infinite line and cylinder. Now in this case we have the infinite cylinder here with the line inside. The line has a linear charge density lambda L, and the cylinder has also a linear charge density, and it's called lambda C. Lambda L is 5 coulombs per meter, and lambda C is 10 coulombs per meter. And the cylinder also has a radius. That radius is equal to 2 meters. And the question is, what is the electric field at a distance r away from the line? There are basically two cases we need to concern ourselves with. So, two cases. We have the radius is going to be smaller than the radius of the cylinder, capital R, or our radius is going to be bigger than the radius of our cylinder, capital R. And we're going to have to treat those two cases separately. But how do we even start? Now in this video I'm going to assume that you're already familiar with Gauss's law and how to use it. And just to reference it, I'm going to write it down real quick. It basically states that the electric flux is equal to the closed integral of the electric field dotted with the infinitesimal area, and that's equal to the charge inside divided by epsilon 0. Then you can also write this part here as E dotted with the normal vector of that tiny area element, and then the area just turns into dA, and that might be useful a little bit later. But the most important thing to realize here is this sign here. And that basically means that we're going to be enclosing whatever object we're dealing with. And what's going to be important is everything inside of the Gaussian surface that we choose, which is why we get the charge inside here as a result. So basically the electric flux is only affected by what is inside the enclosure. And then, by superposition principle, if we have two objects that both create an electric field, that means we can get a function of the electric field for each object individually, and then we simply add them together. We add those functions together as vectors. And if we look at this particular example, we can make it easier for ourselves and look at the cylinder from the top. So this would be our cylinder from the top with a positively charged surface, and then let's say this is the line, which is also positively charged. Now if we have some radius in here, r, that means our Gaussian surface, whatever we're going to choose, is going to be enclosing just the line. So our function is going to be only including the line in that case, and that is the first case we were talking about. Then there's the other possibility. Let's say our radius is outside of the cylinder. Now we have two objects inside whatever Gaussian we're going to end up choosing. We're going to have the line here, and we're going to have the cylinder outside. So we need both of them, and we can add them together as vectors. So let's start with the inside, since that's the simpler case, and since that is going to give us a general formula for the electric field due to the line charge. Now, we're going to be referencing, again, Gauss's law, particularly this part, where we have the surface integral of the electric field is equal to Q inside divided by epsilon 0. Now if we work on the first part here first, we have to ask ourselves a question, which is, what Gaussian surface are we going to use? Technically, any surface is going to do, but there are certain surfaces that preserve the object's symmetry in a way where the problem simplifies greatly. Now, there are only a couple of objects that usually simplify things. Two of those are spheres and cylinders. A sphere in this case wouldn't work because a sphere uh, wouldn't have a constant electric field at all points of its radius, but a cylinder would work. And if I just redraw the cylinder here real quick, I have the line, cylinder. A cylinder would perfectly encompass the line. We wouldn't have to worry about its sides because its sides would technically also stretch out to infinity. So we'd be worrying about the outer surface here along the length of the cylinder, and the radius as you go around this Gaussian cylinder here is going to be constant. And since the electric field depends on the radius, the electric field is going to be constant. That's our first argument for simplification. Then the other thing is that our area elements here is going to be perpendicular to this electric field, to the radius, which means that the normal vector of this infinitesimal area element is going to be parallel to the electric field vector because it's parallel to the radius. And we can rewrite Gauss's law real quick just to make sure we see how things simplify. We have the electric field dotted, and we're going to rewrite it as we did before with the normal vector of the area element. This is a dot. And that is then times by the infinitesimal area element, which is now a scalar and not a vector anymore, because we have the normal vector here. Now the normal vector is perpendicular to the area element, which means in this case, because of the Gaussian we chose, that normal vector is going to be parallel to the electric field vector. So we can write that as our second argument, that the normal vector is parallel to the electric field. Now, if two vectors are parallel, their dot product turns into just a scalar multiplication, which means we get still this integral, and e dot n, because they're parallel, will simply be e, because the magnitude of n is just 1. It's a unit normal vector. So we're just left with e, and we're left with the dA. But we've also made the argument that e is constant, and if it is constant with respect to this infinitesimal area element, it means it can slide out of our integral. And we get e, and now this closed surface integral of dA. Which means in the end we just get the area, whatever area we're talking about. In this case, we were talking about the area of our Gaussian cylinder. And I'm just going to denote that by saying we get E times the total area of our Gaussian. And that concludes the first part of Gauss's law. Now the second part is the Q inside divided by epsilon 0. That's a bit curious because we're dealing with an infinite line here. So an infinite line that has a uniform charge density will have an infinite charge. But what we can do is we can use a linear charge density and refer back to the definition of a linear charge density, which is that the linear charge density is defined as Q divided by L. Rearrange the equation and we get Q is equal to lambda L. So this equation then turns into lambda L divided by epsilon 0. To get the total charge inside, that L will still have to be infinite, which may seem like a problem, but that problem is going to go away in a second. Because now we're going to combine this equation, because we found the left part and the right part here. The left part we found to be this, and the right part we found to be this. So let's combine it back together. We have E times the area of the Gaussian is equal to lambda, and in this case we were talking about the lambda of the line, so let's specify lambda L, times the length of the line divided by epsilon 0. And we're almost done here. The only thing we have left is to figure out what this area of the Gaussian is. Now we don't have to concern ourselves with the area of the sides of the Gaussian. The electric field there is taken as the dot product with the infinitesimal area element is going to turn out to be 0 anyway, because the area's normal vector is going to point up and the radius is still going to point sideways. And two vectors that are perpendicular, their dot product is 0, so that we can completely ignore that part. So the area of the Gaussian that we're interested in is really just the surface here, which we know to be 2 pi r, which is the circumference of a circle, times the length of the cylinder. So let's rewrite this as 2 pi r, although in this case we're not talking about the r, the radius of the outer cylinder, we're talking about r, the radius of our Gaussian, and our Gaussian in this case we haven't set to have any distance, it's just small r. So it's 2 pi r times this fixed length of our line segment. And that is still equal to lambda L times the length of the cylinder divided by epsilon 0. Now to get the electric field inside, we basically just have to divide this part here over. We have E, and now since we're close to the end, I'm just going to call this E inside, just so we can tell the electric fields apart later on. And we get lambda L times L divided by 2 pi, whatever radius we chose for the Gaussian, and then the length again, and epsilon 0. Now we can plug in any radius for our Gaussian cylinder, but we were asked in the beginning at any distance r, so we're going to leave that open. We're going to leave it as just whatever r you want it to be, as long as it's inside of the cylinder, and the lengths cancel, which means we get this final equation that the electric field inside is equal to lambda L divided by 2 pi epsilon 0 r. And that equation holds for any radius if we're talking about just the line. So we can use it for the next part as well, where we're going to concern ourselves with the electric fields of both the objects that we have. So let's move on to the outside of the cylinder. I'm going to redraw the cylinder one last time. Infinitely extending again. And this time we're going to have a radius that is outside of both objects. And in terms of the Gaussian that we're going to use, we're going to be using a cylinder again, for the same reasons as with the line, because our electric field is going to be constant, because the radius is going to be constant as you sweep around. And also because the normal vector of an area segment is going to be parallel to the electric field vector. So we're going to be choosing another Gaussian cylinder, except that this Gaussian cylinder is outside of both objects. And then we refer back to Gauss's law. We have the integral of the electric field dotted with dA is equal to Q inside divided by epsilon 0. I'm going to speed up the part on the left side because we just did that, where we have E constant and the normal vector of the area is parallel to the electric field, so in the end we will just get E times the area of the Gaussian for the same reasons as before. Now we just have to figure out what we get for the Q inside, because we have two objects now, so we have to sum all the charges we have. Before we said the charge inside of the line was just lambda L times the length of the line. And by the same argument, we can also say that we can get the total charge of the cylinder, which is lambda C times the length, which happens to be the same length in this case, because they're both infinite, divided by epsilon 0, and we can simplify that a bit further with L factored out, and we have lambda L plus lambda C divided by epsilon 0. Now we can continue those two parts of the equation. We can develop the area of the Gaussian again, which is still the area of a cylinder. And as before, that turns into 2 pi r, where r is the radius of the cylinder times the length of the cylinder. R is still the distance from the center, except that this equation we're going to get is only valid if that distance is greater than the radius of the charged cylinder. And that is going to be equal to the length lambda L plus lambda C, divided, of course, by epsilon 0. Now we can continue the equation by dividing over this part here. The electric field, and I'm going to name it now, the electric field outside is equal to, the L's going to cancel, and we have lambda L plus lambda C divided by 2 pi epsilon 0 times r. So we've got two results. We've got a result inside, where the E is equal to lambda L divided by 2 pi epsilon 0 r, and we have the electric field outside of the line and the hollow cylinder, which is equal to lambda L plus lambda C divided by 2 pi epsilon 0 r. If you want to be fancy, you can even write this as E being a function that has two definitions, which will be lambda L divided by 2 pi epsilon 0 r if r is less than capital R, which is the radius of the cylinder, and it's equal to lambda L plus lambda C divided by 2 pi epsilon 0 r for r greater than the radius of the cylinder, of the hollow cylinder, and both of those things are part of the electric field. And you may be able to recognize the superposition principle here, where the electric field outside basically looks like it is just a superposition of the electric field that we had before, lambda L divided by 2 pi epsilon 0 r, plus lambda C 2 pi epsilon 0 r. And this part is just the electric field of the hollow cylinder alone, where there are no charged line. And together they give us the total electric field outside. And that concludes this video. I hope you enjoyed watching, and thank you for watching.